I want you to imagine that you have some function, f of x, and that function has two friends. One friend is h of x, and the other is g of x, and one of them is bigger, and the other is smaller than f of x. So here I've got f of x is some general function, g of x is larger than f of x, and h of x is smaller. Okay, I want to know what is happening at c to my function f of x. So as x approaches c, I'm kind of looking at a limit. What is going on with f of x? Maybe f of x is written in such a way that we have an indeterminate form. We can't tell if the limit exists or not. But if I know that f is squeezed between h of x and g of x, then maybe I can determine some information about f of x. And hence we have what we call the squeeze theorem. So f here is being squeezed between h of x and g of x. Okay? So I want to lay out this theorem, describe how it works, and then maybe do an example or two with the squeeze theorem here. So, same picture. The squeeze theorem states the following. If h of x is less than or equal to f of x, less than or equal to g of x, for all x not equal to c in an open interval containing c. Okay, so what that means is h of x is always smaller than or equal to f of x in this interval, and g of x is always larger than or equal to f of x in this interval. So I want you to think about some kind of little window around c, drawn by those blue lines there, and around c then, that first hypothesis is true, right? That h is less than f is less than g. Okay, that's a requirement. It is also required that the limit as x approaches c and the limit as x approaches c of g are both equal to the same thing. And I've just used a placeholder L to describe that. So say h and g are both approaching L as x approaches c. Then the squeeze theorem states that the limit of f as x approaches c exists and should also be equal to L. Okay, so what we've got is kind of f being squeezed between h and g, and because h and g are approaching the same value, we can say that, of course, since f is between the two, it must also be approaching that value. So my picture isn't exactly perfect here. I want you to imagine in that green circle that all those functions there are kind of right on top of each other. F is kind of being squeezed between them. It might be equal to those guys at c or right around c. Right? So I want to exclude the possibility that I'm actually at c, but just in this little small neighborhood around c. So what I want to do here is go through an example of when this theorem might be useful. So let's look at the limit as x approaches 0 of x squared times sine of 1 over x. Okay, so I'm interested to see if this limit exists or not. And what I notice is that, of course, I can't direct substitute because 1 over 0 in my sine function there is undefined. Right? But I still want to think about the behavior, what's going on. As x goes to 0, x squared is going to 0, but sine of 1 over x is kind of does not exist. Right? I don't know. Sine of something that's undefined, I don't have a great idea. Okay? So what I'm going to try to do is maybe find two other functions, h and g, that are smaller and larger, respectively, of this entire function here. And what I want to use is the fact that sine of any angle is always between +1 and -1. Okay? That's always true. In our case, our angle, what we're working with, is 1 over x. Okay, and what I want to try is that inequality I know for sure, and that's going to kind of, set the stage for the rest of this example and hopefully applying the squeeze theorem. So what I want to do is recreate that original function. F of x is x squared times sine of 1 over x. I've got just sine of 1 over x on the right side in that inequality. Well, what I want to try to do is multiply all of that through by what I'm missing, and that's that x squared. It's important to note that x squared is always positive. I should say equal to 0. That's a possibility, of course. There's always greater than or equal to 0. So that means that when I multiply through that inequality by x squared, I'm not going to change the signs, right? There's really nothing I have to worry about with the signs if I'm multiplying by a positive value, okay? So when I multiply through, I'm left with minus x squared on the left, x squared sine of 1 over x in the middle, and x squared on the right. So I'm able to multiply through that compound inequality by x squared, and what I extract from that in the middle, being squeezed, is my original function. Okay? So as long as h of x and g of x, the outsides are approaching the same value, as long as they have the same limit, then I can say from the squeeze theorem that f of x in the middle also has that same limit. So if the leftmost function there, minus x squared, is h of x, and the larger one is g of x, those limits need to be the same. And I can verify that pretty quickly here. Minus x squared, as x approaches 0, also goes to 0, right? And that's, of course, because x is approaching 0. Same thing with g. X squared, the positive version, is approaching 0 as x approaches 0. Easy enough. From the squeeze theorem, then, I should be able to say that the inside also should go to 0. So I've shown that those two limits, h and g, minus x squared and x squared, as x approaches 0, are indeed both approaching the same value. And since this compound inequality, since f is between the two, I can say it also goes to 0. So we should write something like this as kind of our conclusion. By the squeeze theorem, we say that the limit as x approaches c should be a 0, of x squared sine of 1 over x should indeed be 0. Okay. Well, that's just one example of where the squeeze theorem comes into play. I don't exactly know what's going on with x squared sine of 1 over x, but I'm able to kind of pin it from above and below between two other functions that I can tell have the same limit. Okay. The squeeze theorem also gives us two special limits from this, and I'm not going to show you where these come from exactly. You can explore that on your own. But there are two special limits that I obtained from this. The first is that the limit as x goes to 0 of sine of x all over x is 1. And the second is that the limit as x goes to 0 of 1 minus cosine of x over x is 0. Okay, so those are two special limits that the squeeze theorem would help me obtain. Okay. We're also going to show later that the limit as x approaches 0 of 1 plus x to the 1 over x is e. But we'll get to that a little later once we learn some other properties of limits and even into derivatives. I want to do an example here very quickly with one of these special limits. Let's look at the limit as x goes to 0 of sine of 3x all divided by x. So we can quickly, identify that that's very similar to sine of x over x, right? Sine of 3x over x. But there are some semantical differences here, right? My argument of sine is now 3x instead of x. But what I should be able to do, in fact, the x in my original limit there is really just kind of a placeholder for any angle, right? If the argument of sine is going to 0 and I'm dividing by that same argument, then the entire limit should approach 1. So I've got some strategy here. What I'm going to do is I'm going to recreate kind of sine of an angle, an argument, over the same thing. And I can do that. I need to bring a 3 into the bottom to get 3x. So I do that by multiplying by 3 over 3. And what that gives me is 3 times sine of 3x over 3x. Again, now 3x and 3x are the same. The extra 3 that I have to multiply by 1. I don't have a choice. The extra 3 that I have, I know that I can pull out and be left with 3 times the limit as x goes to 0 of sine of 3x over 3x, and I can apply my special limit then. That limit is exactly 1 times 3 should give me a 3. Okay? And it's because those arguments are the exact same. Okay? The squeeze theorem can be used in loads of examples and all sorts of branches of mathematics. These are just a few quick examples, but thanks for watching.